Hello everyone, I am Chandras Misra from ABES Engineering College, Ghaziabad. In this lecture, I am going to discuss a Kruskal algorithm to find a minimum spanning tree. Here we'll see minimum spanning tree, then we'll see Kruskal's algorithm, for example, then we'll see complexity analysis and applications of the Kruskal's algorithm. Now, what is minimum spanning tree? So we know spanning tree is the uh, subgraph of a graph with the minimum number of edges with no cycle to connect all the vertices of the graph. Okay. So let us take an example of this. If what is the minimum spanning tree? As we know that there are multiple spanning trees are possible in the graph. So if the cost is associated with the edges of the graph, or we can say if we have a weighted graph and we want to find out which spanning tree is having minimum cost to connect all the vertices of the graph without any cycle. So in this scenario, we have to find out the minimum cost spanning tree. So let us take this example. Here we have cities, different cities, and we want to connect these cities via roads. Or we have, or we can have any example like we want to connect with optical fiber cable or anything else. So suppose the connections like if we want to connect Meerut and Noida, so we'll have 7 costs associated with this. Like Meerut to Delhi, we have 8, Delhi to Ghaziabad 5. Like this, we have different costs associated with this. Now we can say that there are different way to connect this these cities, but which city is having the minimum cost, we have to find. So in this case, suppose we are taking first we are connecting Greater Noida to Hapur, like this. We are taking this path. After that, we are taking Noida to Delhi. Then Noida to Greater Noida, like this. And after that, Hapur to Ghaziabad. So these outer cities are already connected. Now we want to connect this Meerut from this. If we connect from anyone, will easily reach to any other city. So what we'll do, we'll just select this minimum cost like this 5. So we'll take this one. So now this is our spanning tree, and the cost of the tree will be the cost of will add the cost of each edges associated in this spanning tree. So we'll add this like 2, we'll add 2 plus, we'll add, so here we can add 2 plus 3 plus 4. Again we have 4, this one, and then we have 5. So total cost is around 18. Okay. So this is the minimum cost of this spanning. Now we have applied our brute force approach and we have find out the minimum cost spanning tree for this. Now we'll see Kruskal's approach, Kruskal's algorithm to find out the spanning tree. Suppose we have this graph. So before going into the details of these steps, first of all, let us know what are the steps to perform this. So step one is we will just step one is we'll sort all the edges of this graph in non-decreasing order of their weight. So we'll sort edges, okay, on the basis of their weights associated with this. So we'll sort edges. These are the edges in their increasing order of their weights. And after that, in step 2, what we'll do, we'll just find out the minimum age from the set of edges, and we'll try to uh, connect or try to find out this spanning tree. So one by one, we'll step 2 will find the minimum age, find minimum weight s, and add to spanning tree. Add to spanning tree if no cycle, if no cycle is there. If after connecting this there is no cycle, then only we will add this graph, this edge. Otherwise, we will discard this edge. And step 3 is will repeat this process. Will repeat step 2 until all the vertices are connected. Okay. So let us begin with the numerical problems. How can we solve this issue? Okay. So suppose we have all the vertex. We have a forest of vertices. Like here we have 7 vertices, and after that we'll just take all the edges in the ascending order of their weights. Okay. So here we have all the edges in the ascending order of their weights. Okay. So what we'll do, we'll just take the edge with the minimum edge with minimum weight. So here we can see here this is 1/6 is having minimum weight, that is 10. So we'll take this, and we'll say the edges, the vertices of these edges 1 and 6. 1 is 1 as U, and 6 as V. Now this is our task to find out whether U and V are belonging to same tree or not, or same set of vertices or not. So here we can see here, if we have a set of vertex like this, we have 1, 2, 3, 4, 5, and 6 and 7. So here we have different sets. So 1 is belonging to different set, and 6 is belonging to different set. So there is no issue. We can connect 1 and 6. So we'll just connect this 1 and 6. In the second step, we'll take second minimum is, that is the 12, and the edges are 3 and 4. Now again, and after connecting this 1 and 6, what we'll do, we'll just merge this 1 and 6 as one set. So after doing this, now 1 and 6 are in the same set, and 2, 3, 4, 5, 6, 4, 5, and 7 are different set. Now next is 3 and 4. So U is 3 and V is 4. Now before connecting this 3 and 4, we have to check whether 3 and 4 are belonging to different sets. So yeah, we can see here 3 is belonging to different set and 4 is in the different set. So we'll connect this 3 and 4. So we'll connect this 3 and 4 and merge this. We'll take the union of this set. So now this set will become 1, 6, 2. Now this will become 3 and 4. After this, we have 5 and 7. Now we'll take this is which is 14. So vertices are 2 and 7. So before going to connect this 2 and 7, we will take we'll see whether 2 and 7 are belonging to different sets or not. So yes, these are belonging to different sets. So we'll just connect 2 and 7. And we will write cost also associated to this. 1, 6 is 10, 3, 4 is 12, and 7, 2 is 14. Now we'll merge will take union of this. So now we have 1 6, then we have 2 7, we have 3 4, and we have 5. Okay. Again, we'll take this 2 3. Now, before going to connect 2 and 3, we will take whether 2 and 3 belonging to different set or not. Yes, 2 belong to this set and 3 belong to this set. So there is no issue. We'll just connect 2 and 3 with the cost of 16. And now we'll merge uh, this set because now 2 3 uh, is the vertex 2 3 is uh, in the same set. So we'll take the union of these sets. Okay. So now we have 1 6, 2 uh, 2 7. We have 2 7, 2 7, and 3 4 in the same. And now we have 5. Now come to this 4 7. So if we are going to connect 4 and 7, before that we have to check whether 4 and 7 belong to different set or same set. So yeah, clearly here we can see the 4 and 7 are belonging to same set. So it means if we connect this 4 and 7, 4 and 7, 4 and 7, definitely there will be a cycle. So what we'll do, we'll just discard this edge 4 and 7, will not connect in this. Now come to 4 and 5. So we'll take edge 4 and 5. So here 4 and 5, definitely 4 and 5 are belonging to different sets. So there is no issue. We will connect 4 and 5. So there is no issue. We'll connect 4 and 5 with the cost of 22. The cost of 22. And now we'll take the union of this. So in our first, we have to set 1 6, and this will have 2 7, 3 4, and 5. Now come to this S, which is 5 and 7. So we'll take 5 and 7. If we see here, 5 and 7 are belonging to same set. So we'll discard this 5 and 7, will not connect in this one. Now come to 5 and 6. So we can see here 5 is U and 6 is P. So if we run find set, we'll find. So 5 and 6 are belonging to different sets. 6 is in this set and 5 is in different set. So there is no issue. And we can connect 5 and 6. So we'll connect 5 and 6. And the cost of this 5 and 6 is 25. So we'll connect this. And now what we'll do, we'll just merge this. And we can see we have covered all, we have only one set, and we have covered all the vertices, or we have connected all the vertices. So this is the minimum spanning tree with the cost. If we find out cost of this vertex, it will be this minimum spanning tree. It is 10, 12, 10, 14, 16, 22, and 25. So this is the we will add up this. So we'll find out the total cost of the this spanning tree. Okay. Now the question arises: what is the complexity of this algorithm? So we can see to sort. First step, what we are doing, we are sorting this. For sorting, we'll take there are a number of edges, e number of edges. Suppose there are e number of edges. So to sort this, we will take e log e. E log e is used to sort this. And after that, to find out whether there is cycle or not in the in any age, for that we will take log v, to find out, to find cycle, whether there is cycle or not. Find set will take log v, and we are calling this log v for each edges. So it will be e log v. So overall, if we take the time complexity of this, it will be e log e plus e log v. So Basically, we can see here the log v and log e. So maximum edges can be v square. So this factor is not significant for it. This we can take, we can say log e and log v are same. So we can say the complexity of the running time of the Kruskal algorithm will be e log v or e log v. Now come to the part is space complexity. So for storing the vertices, we'll take order of p, and for storing all the edges, we will take order of p. So space complexity will be order of p plus e, and it is very useful for finding the the minimum spanning tree. And as at a, but there is a problem at every time it is not a connected graph. We have a forest and we are just connecting these forests on the basis of the edges. We are connecting to forest or to vertices of the forest if they are not belonging to same set. Because we are going to avoid cycle. If there is any cycle after connecting the edge, we'll just discard that edge. So this is main thing here. Thank you for watching this video.